Okay, so let's start the journey. So today we're gonna speak about performance in the web, and we will be sharing the outcomes of a research that we have been doing together with Danny for exploring new tools that can bring improvements or new opportunities to bring performance improvements to the web. And this tool in concrete that we've been researching is WebAssembly. This is us. It's a shared presentation. Danny will be doing the last part a bit more hands-on. We are both senior software developers at Dynatrace. Dynatrace is a software observability company. We do many things, observability, security, and so on. If you want to know more about us, there's Alex around here, or he should be. There you go. So you can approach him. Okay, so what do we do? In this case, we work as a front-end developers, and as a front-end developers, we are basically working with one programming language, which is JavaScript, right? There is this attributes law that says that any application that can be written in JavaScript will eventually be written in JavaScript. This is becoming more and more true. But JavaScript, apart from the huge, ways that it has come, has improved a lot since its inception. But the history of JavaScript is it was not developed to be the programming language, the most widely used programming language in the planet. It was developed in the 90s for a really early version of the web, and it took actually 10 days to develop. So you can imagine that it was not developed to have this kind of scale in mind. And a lot of work has been done regarding engines and so on. So now it has become like a really quick language, really flexible, and really holding a huge ecosystem. But it was developed in a time where the web looked like this. And it was done to basically do some scripting on forms and so on. So it has its flaws. So what are we going to talk about? We want to talk about this kind of new technology. It's from 2017. It's called WebAssembly. And WebAssembly, it's not actually assembly language, even though the name states so. But it's a kind of it brings us much closer to the iron of the computer. So it means that it has much less complexity than a scripting language such as JavaScript, and thus is much leaner, much faster, and can do things that JavaScript is not optimized for, such as image processing, music editing, and this kind of native performance that we need for more complex tasks. But this is really new. There has been some attempts before at doing things like that, such as Java applets, ActiveX, and now this is Flash. So there were kind of browser extensions or plugins that we used to use to add extended features to the browser. But what's the main difference with WebAssembly or Wasm? Well, Wasm is actually born with web in mind. So it's actually thought out to be executed in the browser, and it's actually embedded in the browser. And this is, I would say, the main advantage. So what is it? It's a binary instruction format that serves as a portable compilation target for high-level programming language. This is a nice bunch of words here. But what it means is basically that it's a target, a compilation target. So it's actually not a language. It's an execution format to which you can compile other languages. And it provides a set of instructions that the browser is really able to take and optimize and deliver to the processor in a very low-level way, so you can get native performance within the browser context. It is sandbox, which means that it has its own runtime and it's kind of isolated, which is really important for security in the web. It's language agnostic, and this is, I would say, one of the, if not the best advantage. You don't code in WebAssembly, you code in C, C++, Rust, even interpreted languages such as Python. You can actually, but I will go into that later. But basically, you code into other languages. Your source code is done in another language, and then it's transpiled into WebAssembly. Another advantage is the ecosystem, right? Because we are in the web, it's where I would say most of the developers are. So you're leveraging a very big community of people that are starting to contribute and will potentially contribute in the future. And this is a really important point also, it's an open standard. So there's not a private company behind it. So you are not exposed to the economic or political interests of an institution. It's more of a, a worldwide web consortium-led initiative where there's like a standard that is being exposed to be used publicly, right? So what is the main advantage of Wasm? So of course, the selling point is performance, right? It brings a performance that is, as I said before, something that you could only imagine outside of the browser, never within the browser. So you could play high-performance games, you could do like Photoshop editing, video editing, all these kind of things that were not thought out to do within the browser context can now be done with WebAssembly. There are other things, such as, for example, security, since it's something which is embedded in the browser. You're not playing with third-party extensions, so to say. So, of course, this is going to be super tested and so on. And I would say another really strong selling point is the interoperability. So you don't have to learn a new thing. You're going to program in one of the languages you know, and you're going to compile actually to WebAssembly. But without support, right? Because if we don't have support for what we do, actually the users are not going to be able to reach our products. So I have this link here which will help us with answering this question. This is actually the current state of art for WebAssembly, right? We see that all latest browsers are supporting, all latest version of the browser are supporting WebAssembly already. We have Internet Explorer here as outlier and Opera Mini, but I mean, not folks that we care a lot about. So we can be really sure that if we do a bet on WebAssembly, it's going to be able to reach a wide audience. And how to use it. So there are basically two ways. The first one would be to use compiled language, such as can be Rust, C, C++. You would develop your source, or you would use source code that you have already developed, and you basically compile it into a WebAssembly format. So it's basically setting the target to a format that is going to deliver a file that is going to be in WebAssembly format, and it's this file that we can deliver to the browser and we can interpret. But as I said before, even with languages that are not compiled, such as Python, which I would say is the main container to JavaScript as the most widely used language, especially with all the machine learning stuff that goes on and so on. So even those languages, we can have tools or libraries that can compile just in time and deliver to the browser the execution runtime of these languages, so to say. We have a demo here of a tool. It's called VMware. They call it precompiled language runtime. Okay, so we have here like PHP, Ruby, Python, and you can basically embed these tools into the browser, and you're going to be able to escape the restriction that currently browsers have, which are JavaScript runtimes. You can insert any other language into your browser and create basically a runtime there. There's a demo that we can check. This is a project which is called PyScript, okay? And we have examples here. For example, a to-do app done in Python and run straight in the browser. So this is going to download the Python source code, it's going to run it, and this just-in-time compiler for WebAssembly is going to take this Python code and understand the instructions and be able to translate it in real time into WebAssembly and deliver it to the browser so you can execute actually Python in the browser. And here you have a to-do list done in Python. There is a trick here, there is a catch. WebAssembly is not able to communicate with the DOM. So this that we just did here is not possible only with WebAssembly. But there is a communication layer, there is an API between JavaScript and WebAssembly, so you can actually call JavaScript functions from WebAssembly, and then thus you can access the DOM. But Danny will tell you later about this because this is a very important thing to consider regarding performance.
Yeah, totally. Y do you use interpreted that works? I mean, does testing time compilation? Or it does perform better but just using JavaScript?
Mm-hmm. It's probably not performing better in this case, but it would allow you to use code that you have existing straight in the browser. So maybe if you're not so interested into performance but want to reuse some business logic that you already have in Python, you can do it. I would say I did add the disclaimer at the beginning, but we are not experts in the topic. We are sharing the outcomes of our research. So I'm answering from my own let's say assumptions. But I think that would be a good result. Exactly. If you have a binary that it goes straight to web, because otherwise you need to execute the interpreted language in the regular fashion. Okay, so once we have that solved, how we use it, I'm gonna just finish my part sharing what I think is the most interesting thing going on right now in this ecosystem, which is a project called Wasm. And what Wasm does is actually the same as Node took the JavaScript runtime out of the browser and was able to bring it to the server. Wasm is doing exactly the same for WebAssembly. So what does that mean? That you can run WebAssembly in any host and basically perform things that are not browser specific, such as accessing the native hardware of the server, for example. And I think, I'm not the only one thinking, but actually the creator of Docker thinks it also. I think that this brings the possibility of having like this consensual and standard runtime environment that Docker, the problem that Docker wanted to solve, basically. Now that if you have a layer that is able to understand or be the compilation target of any other language, you can have like this standard way that maybe the kind of thing that the JVM wanted to achieve in Java can be, this can be a potential candidate to actually achieve it for real and be this standard for executing serverless code and CDN and so on. And with that, what about the community, right? If we don't have a community of people that are actually putting brain power into this is not gonna go anywhere. So as I said before, and of course this is kind of new, the kind of projects that you find in GitHub range below 70 and 2,000, 3,000 stars, not something super impressive. But of course, this is leveraging the community of the web. So I think this has a good chance of having an exponential growth in the future. And there are some projects that already retrieve the kind of initiatives that is going on. I mean, Adobe is creating already Photoshop software for being run in the browser. Unity is making already games in the browser with Wasm. And there are even Java front-end frameworks that use Wasm, Node, .NET, many things going on. So yeah, I would say it's quite an interesting thing to explore. And if you get interested in it now, I would think that you're gonna be quite early on the topic. And this is it on my part. So Danny, if you want to come over.
Thank you, Santi. Well, so as it has been said,
there's a community behind WebAssembly. There are many applications that have been ported to Wasm already. For example, Figma, AutoCAD, Google Earth. VLC is also on the web. And who likes to play chess in here? Okay, 3. Do you use which site do you use to play chess? Chess.com? Chess.com, everyone? Okay. Do you know about Lichess? Lichess is an open source platform for playing chess, the biggest open source platform. Also, Magnus Carlsen, that's the world #1, plays often in there to support it. And Lichess actually has the Stockfish algorithm, but ported to WebAssembly. Why this is important? Because on chess, there's a lot of variation. So from the initial board, you can have multiple combinations that can lead to the win or to the lose. You need a lot of computational logic to calculate them all. So we need fast algorithms in order to do that and calculate all the tree that is behind every move. And there's here open source in GitHub this stockfish.wasm algorithm that anyone is free to use in their application. So what we found is that some guy has created a cheater for chess.com using this algorithm from Lichess. This cheater is kind of a Chrome extension that I have in here. Extensions I have installed in here. And now if we go to chess.com, we can here have our cheat menu that is created from our extension, and it's telling us which is the best move, which is moving d2 to a5, which is moving this bishop in here. So I check the king and the computer moved the king. So now it's telling me that a1, c1. So I should move this tower here, and we can move on. And this actually is the real algorithm. So, okay, he sacrificed the queen. So this is g1 to g2. I killed the queen. I'm fine. And, well, this is a real example of using WebAssembly for improving the performance, because as you can see, the best move is calculated very quickly, even though it has a tree depth of 14. So it's calculating 14 moves up front. Then, more things. There's also this JS-DOS library, which it's built on WebAssembly, and it allows you to port games, old MS-DOS games, into the web easily. There is a huge repository of all the games that have been ported with this library, and we did a try as well of porting the Digger game. That's it. So here on our Dynatrace application, we have the Digger game as well, which has been ported thanks to this library, and we don't need to create it again from new code. More stuff. Okay, this is very cool, but let's see how actually WebAssembly is working on low level and in the code. So for doing that, what we have done is some performance tests of different algorithms to check if it's really true that WebAssembly is more performant. So here we have the Fibonacci algorithm, which is a very straightforward algorithm, which given a number, it calculates a number of times the sum of the previous value and the second previous value in the array. So it basically, you send an integer and it returns an integer. So if the n is 35 and we do this algorithm 10 times, let's see what happens with JavaScript and with WebAssembly. So WebAssembly in this case is much more faster. We can try to do it with a bigger number and it goes exponentially slower. So in this case, Wasm is 3 times faster. And well, let's take a look at the code, how this actually works. So we have here our JavaScript function, which we are calling it directly, and we are sending the number n. And we also have here our Wasm function that we are calling like any other JavaScript function. We just do Wasm export.fit. That this is an object we created here on. We are just fetching our Wasm compiled fit that we have in the assets. It has been pre-compiled before the application was built. And with that, we instantiate our WebAssembly instance, setting it a memory, and we are able to access the code that we've written in C, and we are using the same namespace for the fit function, and using it like this, like any other JavaScript function. So this might prove that the performance of WebAssembly is better than JavaScript, but let's take a look at another algorithm, like the collision detector, which would be an algorithm that given multiple spheres, it detects how many collisions are in the map. So given an array of positions and the radius of each sphere and the number of spheres we have, it will return how many collisions we have in the map. So if we run this algorithm with 2,000 spheres and we repeat it 100 times, let's see what we have. Wasm, in this case, it's faster, but not much faster. In this case, it's almost the same. It's almost the same. So what happens here? Below the scenes, if we take a look at our collision detector, we are calling here the Wasm function, passing the positions, the radiuses, and these are not primitive values. These are arrays. So these arrays are actually, when sent to WebAssembly, are serialized. So we are doing a copy of those arrays, and that's why the overhead that this copy is causing is making it not as performance as it should be. What we could do in this case is playing around this WebAssembly memory, some kind of shared array buffer, which would be a memory which is shared between JavaScript and WebAssembly. And using that memory, we will be able to not be copying every time our array and accessing it from both sides. So we can have also here, we can see how the browser translates the Wasm file. So it looks a very bit like a assembly code, very low level, where you have how many bits our integers have, and very assembly look-alike code. So this is what I've done. We previously compiled like with Mscripten or any other tool we are able to compile to Wasm. And this Wasm file, we are able to export it to JavaScript. So conclusion, What can we do? Should we take into consideration WebAssembly? Well, WebAssembly is very useful to reuse code from other platforms to not having to repeat this code. You will need some extra work in order to make it compatible with WebAssembly, of course, but it doesn't mean that you need to rewrite it from scratch. But also the engines of web, of the browsers of Chrome, Firefox are also very optimized to JavaScript, since it has been the language in the web for more than 20 years. So on some cases, the performance might not be as good as we should compare to WebAssembly. And also the problem about the serialization that we said, if you are copying objects, it will cause a big overhead, so it won't be worth to do your algorithm in WebAssembly. But since it allows you to write on languages that you have your own managed memory, so you control how you manage this memory, you allocate beforehand, you free the memory, you have the capacity to build very performant algorithms with WebAssembly. And that's about it. Thank you, everyone.
Next slides.
Yeah, and by the way, Alex can explain better maybe, but we have a talent community in Dynatrace. If you want to join it and maybe join the discussion there, having the chance to join a process sometime, it's available.
Any questions?
I do.
Yes?
It's to properly. This is a whole process in the client computer. So, I mean, this is not exactly assembly, so you don't have like direct execution in your hardware. I mean, if you are using an RM or some kind of them Wasm app, I don't know, but it's not that hardware specific. It's something more related to the browser, like being adapted, a kind of Java,
Yeah.
what I mean?
The browser, since 2017, it has the WebAssembly API that already handles this for you and is able to read WebAssembly code.
It's more of I think that the step of adapting to the actual hardware is there, but I think you can think of it as like the Java virtual machine, which abstracts this and then on the low level delivers having in consideration the architecture. I'm not fully sure what I'm saying, but I think that the browser is able to eventually release the binary for the execution that is specific to the architecture that you're executing.
Okay, so maybe the performance is relative to the client. I mean, the hardware of the person who is executing the browser, than that a server or.
Yes. The performance will be taken into account in the client. There's also Wasm to the server, so you can write WebAssembly for server. But in this case, what we tried is some precompiled WebAssembly running it on the browser. So the scenario was the same for JavaScript and for WebAssembly. So in Fibonacci, it was much faster for WebAssembly, but in the collision detector, it was more or less even due to the overhead, and that the browser is more optimized for JavaScript, even though it can be slower.
Okay, and last question. Do you know if these guys do plan support some kind of GPU instructions, like for image processing or machine learning or this kind of stuff? I'm not sure if you know, but maybe.
No, I don't know. I know that TensorFlow is one of the.
That's why I'm asking, because I saw them. So probably maybe there is like an approach to.
Yeah, there's a website made with WebAssembly, and there's here a list of many applications that have been ported to to WebAssembly. So here you have details about TensorFlow. You can take a look. I'm not an expert on TensorFlow, but
Neither.
if you are interested, you can try to look at it.
Okay, thank you.